So in the previous part of this lecture, we discussed on how to estimate the population parameter, basically the population mean, using our sample mean or sample statistic if we know the population standard deviation. However, as with most cases, the population standard deviation is not always known. So if we do not know what the sigma or the population standard deviation is, what should we then do? So there are three possible cases where we need to estimate the population mean while we do not know the population standard deviation. And these are the three cases. So the case one is we do not know what is the population standard deviation. We have a small sample size, but even though we have a small sample size, the population from which the sample is selected is approximately normally distribution, or rather normally distributed. And the second case is we have a population standard deviation, again is unknown, and we also have a large sample size. And the last case is a small sample size but not normal distribution. Now, what should we do in these three cases? So if you do not know the sigma or the population standard deviation, case 1 and case 2, where case 1 we have a small sample size but it's a normal population, and you have a large sample size, the way that we estimate it is the same. We are going to use the t distribution. So some people will tell it's that student's t distribution, or some people simply call it the t distribution. We are going to use the t distribution to estimate our mu. This is the counterpart if in the previous scenario, if the sigma is known, we have been using the normal probability distribution. Now, this is now the case where we have your unknown sigma or unknown population standard deviation, and that means this time we are going to use the t distribution. And then for the case 3, it's a small population and a non-normal population distribution, and that is why we have to use non-parametric methods. However, again, this will not be covered here. We are just going to focus on the use of the t distribution to estimate the population mu, or the population mean. Now, what about the student's t distribution, or the t distribution, or some from some textbooks, especially the old textbook, we would say it's the student's t distribution, not because it's usually used by students, but rather the person who developed this one, William Gosset, has a pseudonym named student. So anyway, the t-distribution is a specific type of a bell-shaped distribution. However, contrary to the normals, our standard normal distribution, this has a lower height and a greater spread than the standard normal. So as the sample size here become larger, the t-distribution approaches the standard normal distribution. And the t-distribution has only one parameter, and that parameter is the degree of freedom. And we usually calculate the degree of freedom as n-1, or the sample size minus 1. So the mean of the students, or the t-distribution, is equal to 0, and its standard deviation is the square root of the degree of freedom divided by degree of freedom minus 2. So here is a comparison of your t-distribution and the standard normal distribution. As you can see, the t-distribution is generally flatter and has a wider spread, and this is our normal distribution. So it is that's one of the differences. However, if you have larger and larger sample sizes, this t-distribution, this flatter dark blue curve, will then approach, or will have it will become taller and taller and approach what the normal distribution is. So let's have an example. What's the value of t for 16 degrees of freedom in a 0.05 area in the right tail of a t-distribution curve? Now, this is how we read the t-distribution table. So this is available at the back of the textbooks and also available during exams. Now, unlike the z distribution or the normal distribution table, whereas the value of z is given as the ends, or as the anchors, the headers of the table, and the cells or the data inside the table is the area beneath that particular point. For a t distribution, on the leftmost column is our degree of freedom, And the area under the right tail of the tree distribution curve is the header. And these individual points here are the points in the T, or the number line, the horizontal line. So these are the points T that corresponds to a certain area under the curve. So for example, if you want to know from our example here, the T value for an area 0.05 to the right. So the area beneath the curve is 0.05. So we're going to look at it at the header, unlike the normal distribution where the area is the column, or the cells, the actual data in the cells is in the header. So the area is 0.05 and the degree of freedom is 16. So the value of T here is 1.746. That's the point T, or the point in the number line T. So that's 1.746. So to give you a proper look, so this is the T, the values of T here. The area underneath is 0.05. So this area here is 0.05. This is from the header. The degree of freedom is 16. And we are looking for this point, 1.746. So that's one of the main difference when we look at the Z, the normal distribution table, or the Z table, and the T table. Now, area to the left, area to the right. And then for the area to the left, you're just going to get a negative of the value of T. So how about applying the confidence interval using our T distribution? So for a certain percent of confidence interval for the parameter, the population mean, this is actually very similar to how we do it previously when we know the population standard deviation. The only difference here, instead of using the Z value, we are going to use the T. And instead of using the normalized population standard deviation sigma, we are going to use the sample standard deviation normalized. So when we say normalized, that is, this is the sample standard deviation S divided by the square root of the number of samples. And the value of T again is obtained from our T distribution table. And here, our margin of error is actually the T times the normalized sample standard deviation is our margin of error. So let's have an example. So this is according to a 2019 Kaiser Family Foundation Health Benefits Survey. The total mean cost of employer-sponsored family health coverage was $20,576 per family per year, of which workers were paying an average of $6,015. A recent random sample of 25 workers from New York City who have employer-provided health insurance coverage paid an average premium of $6,600 for family health insurance coverage with a standard deviation of $800. So we want to make a 95% confidence interval for the current average premium paid for family health insurance coverage by all workers in New York City who have employer-provided health insurance coverage. Assume that the distribution of premiums paid for family health insurance coverage by all workers in New York City who have employer-provided insurance coverage is approximately normally distributed. So let's just assess our problem first. So we want to have an estimate within 95% confidence interval. What is the premium paid for the insurance coverage? And our curve is normally distributed, but we do not know the population standard deviation, but we do have a sample of 25 workers, so our n is equal to 25. So if we have unknowns of population standard deviation, but we have n is equal to 25 sample size, so that's less than 30, and a normal distribution or approximately normal distribution, it falls under case 1, and we are going to use the T distribution to estimate our population parameter. So again, sigma is not known, n is less than 30, population is normally distributed. This is case 1. So how do we actually calculate for the confidence interval? So using the T distribution, our confidence level is 95%. So let's first get the normalized standard deviation, because again, our range or our error is T times the S sub x bar, or rather the normalized sample standard deviation. So the normalized sample standard deviation is equal to the actual standard deviation 800. This is this is the sample standard deviation divided by the number of so it's not supposed to, sorry, it's not 250, it's supposed to be 25. So our degree of freedom, to get our value of t, our degree of freedom is n minus 1, which is 25 minus 1, or 24. Now, how about the area beneath the curve? Now, the area beneath the curve here, because we are just going to approximate our sample, so it falls between the extreme left and extreme right. So for getting that area beneath the curve, we are actually getting, so we want it to be 95% confident. This is a rather the solution given here is rather convoluted, so we can just simply say we are at 95% confidence interval, correct? That is equivalent to 0.95 confidence. So 1 minus alpha, sorry, that is 1 minus alpha. So our alpha is 0.05 because 0.95 is the 1 minus alpha. So we have 1 minus 0.95 is 0.05. Divided by 2, we get 0.025. And that is the area beneath the tail. Why do we need to divide it into 2? We need to divide it into 2 because we are getting because the total area beneath the tail, we actually have two tails. So we have the extreme right and extreme left. And that's why we have to divide it by 2. Because the total area from the extreme left and the extreme right should be equal to 0.5. And that is actually the reason why we have to do that. Now, the value of, sorry, not 0.5, 0.05. Because that's 1 minus 0.95 is 0.05. 0.05 divided by 2 is 0.025. And that is the area that we are going to aim for. Using the table, we are going to look, the area beneath the curve is 0.025. So the value of t here is 2.064 from the table. So I won't be showing you the table anymore. And then we are going to estimate the interval, the confidence interval. So x bar is our sample statistic. This is the sample mean, that's 6,600, plus minus our margin of error. Our margin of error is equivalent to the value of t beneath a 0.025 area on the right side and on the left side. But anyway, it's the same because it's just plus minus. So you have your 2.064 times 160. This is our normalized sample standard deviation, S sub x bar. So plus minus this value. So our confidence interval, or we are confident, 95% confident that the mean, the average amount is between, or falls between, $6,269.76, so $6,930.94. So the answer here, or the statement of the answer is I can state now that with 95% confidence that the current mean premium paid for family health insurance coverage by all workers in New York City who have employer-provided health insurance coverage is between $6,269.76 and $6,930.24. So that's calculating or rather estimating our parameter, our population parameter, using the student's t distribution, whereas we do not know the population standard deviation. So here is the view of what I was talking about a while ago about the 0.025. So because the 95, when we say 95% confidence, here is the 95% confidence. So here is the remaining area. That means this is the error estimates, or the probability of getting a wrong answer or a wrong estimate here. And it pertains to both left and right side, because the question doesn't really say that it should be greater than or less than. So it just say within a certain interval. So it's equally distributed into two, the left and the right side. So the total area here should be 1 minus 0.95 or 0.05. And that's why on the left side, it's 0.025. On the right side, it's 0.025. So if you add them, it's 0.05. And that is the error how high the probability of getting an erroneous estimate is. So that's basically it. So let's have another example. So we have 64 randomly selected adults who buy books for general reading were asked how much they usually spend on books per year. So the sample produced, our sample of 64 people, let's say n is equal to 64. So the sample produced a mean of 1,450. So this is our sample mean, and a sample standard deviation of $300 for annual expenses. So how we want to be 99% confident that using this statistics or this sample statistic, we can estimate the population, the average amount of spending on books per year of the general population with 99% confidence. So sigma is not known. Our sample size is large. It's 64. So it falls under case 2. So we can still use the student's t distribution. So our n, our number of samples is 64. Our parameter, or rather our sample statistic, is 1,450. Our sample standard deviation is 300. And we want to have a 99% confidence level. So getting the normalized sample standard deviation, I just get the standard deviation divided by square root of 64. That's 37.5. And now for the t value. So the area beneath the tail is, we are at 99% confidence. So 1 minus 0.99, that's 0.01. Divided by 2, you get 0.005. So that's the area beneath the tail of the leftmost tail and the rightmost tail. So using the table, we are just going to get what would be the t value at 0.005 area, given that the degree of freedom here is 63. Degree of freedom again is n minus 1, or the number of samples minus 1. And so we have a value of 63 and 0.05. Use that in the table, you will get a value of t of 2.656. So calculate now our interval. So our margin of error is t times the normalized sample standard deviation. So just plug it in the equations, plus minus our sample mean, x bar, or sample statistics, our point estimate. And we now have an estimate at 99% confidence. So that means we are 99% sure that the amount of annual spending of adults on books, based on our sample, the annual spending is around this range, 1,350.4 to 1,549.6. So that's the range of spending that we have. So again, the statement for the answer here is, which usually, if you haven't noticed yet, usually when we have when we answer statistical problems like this, we must also include the percent confidence. So we can state that we are 99% confidence that the annual expenditure by all adults who buy books is between 1,350.4 and 1,549.6. So that's our solution, or that's our final conclusion or answer. Now, this is for smaller samples. What if we have a large sample size? Because again, the t distribution can only allot a certain amount of value. So for a very, very large sample size, we can use the final row for the table, which is your basically the infinity symbol. And or we can just use the normal distribution as an approximation. Why can we use the normal distribution? Because remember, if we have very, very large samples, as stated, the t distribution approaches the shape of the standard normal distribution, and that is why we can use the normal distribution to approximate our t distribution. And that's it for this part of the lecture. So in the next part, we will talk about population proportions for large samples.